Welcome. My name is Mathilde Avon. I'm a chemical engineer. I work at Coolrec. This is a WEEE recycling plant, so waste from electrical and electronic equipment. In the Creator project, I am leading the work package regarding identification and sorting of brominated plastic. This presentation was made for the Plastics Circularity Multiplier event. That's pretty much it for the introduction. Let's start. Compliancy and recycling. This is two words that people don't really associate together. You're probably going to ask me why. Because those two words lead to one simple question. Are recycled plastics safe to use? Well, let me tell you, that's quite a controversial question. I could tell you the answer right now. The answer is yes. But you're probably going to tell me that my opinion is literally biased because I am making recycled plastic. So today, I decided to present the facts and demonstrate that sorting can be part of the solution. Today, I'll present the sorting model that we are doing today, so a little bit about the state of the art, what we are doing at Coolrec, and then I'll move towards the process of the future, the process of tomorrow, what we plan to develop and design in the Creator project. So let's dive in. A little bit about the background. Why is it so challenging to recycle? And especially this plastic from the waste from electrical and electronic equipment. First of all, because it's quite a complex stream. As you can see on the slide, there is a lot of different polymers that are existing in this stream. There is the styrenics, there is the technical plastic, there is also the polyolefins, so that makes quite a lot of polymers. And then, in addition, we have also the flame retardants, the fillers, the pigments that can be in there. And if we make the math, without all of those combinations possible, well, that's quite a lot of possibilities. Then if we look at the timeline, when we release an equipment on the market, let's say in 2000, when it's reaching end of life, the equipment is discarded. It's in 2020. Afterwards, the same year, it's entering the collection system and it's treated in a recycling facility. When the equipment was put on the market, it was containing some substances, for example, fire retardant substances. The thing is that 20 years later, when it's entering the recycling facility, this substance was studied a lot and it's transformed into a substance of concern because it was entering the legislation. What the recycler has to do is to separate the plastic containing substances that are restricted from the rest of the plastic. And that's quite a challenge. What do we plan to do in the Creator project? The Creator project has three main axes. First, we need to collect, then purify, then reuse the material. So it's taking care of the complete plastic loop. The polymers that are focused in this study are the ABS, the PC-ABS, and the PS. In the market that we are taking care of, we look at construction and demolition waste, electrical and electronic waste, and aeronautic waste. And the plastic that we will recover will be reused in automotive markets and also aeronautic markets. So here is the question of today. Is there a match between the complexity of the stream and the compliancy to the European legislation? Well, we will see how sorting can be part of the solution. This is a little bit about the state of the art. So what we are doing at Coolrec, a WEEE recycling plant. So annually at Coolrec, we treat around 31,000 tons of plastic. By plastic, I mean the waste plastic, so the one you can see on the slide. Here is the process. First of all, we have this waste plastic. Then we go through metal separation. We will remove the remaining metal and recover them. Afterwards, we have a density bath where we remove the heavy plastic. This, we will go a little bit deeper on this fraction afterwards. Then we have a granulation step where we'll reduce the size of the plastic. Then a suction system where we remove the light fraction. Then a density bath, and we have actually several, so we call it a waterfall of density bath, where we remove styrenics. And this is where we can add some more sorting steps in order to reach a higher purity. For example, electrostatic separator, color separator to be able to produce white recycled plastic, but also rubber separator to remove any rubbery impurities that could be left. And at the end, we have a granulation or compounding step to enhance the mechanical properties, where we can bring a granulate on the market that can go back to. So this is a little bit the state of the art of what is doing today in mechanical recycling. If we look at this heavy plastic fraction, inside we have some heavy plastic. We have to remove them because that's the plastic that are not compliant with the REACH regulation. And as a recycler, we have to place back on the market some plastic that are safe, so REACH compliant. So we remove them from our stream and send them to waste incineration. Inside, we have some plastic with brominated flame retardants, such as the ABS and the PS. But unfortunately, there is also some technical plastic that we could recover. But in order to be on the safe side, we remove them via this density bath. And this is why we have to work in this fraction. And this is the focus fraction of the Creator project. So what is the sorting challenge? What do we have to put in place in this sorting system? First of all, regarding the material, we need to detect the ABS, the high-impact polystyrene, and the ABS-PC. We have a requirement on the particle size between 40 and 60 millimeters, and we have to be able to handle a wet material. Then regarding the substances of concern, we don't only target the brominated plastic because there is way more in the regulation than only brominated containing plastic. Therefore, we decided to target the heavy metals like the cadmium, lead, chrome, but also the chlorinated base flame retardant that are also restricted in the regulation. Afterwards, let's look about the process. We need to see black plastic. In electronic, there is so many black plastic that we have to include them in our process. Then we need an automating sorting process because we need a business case that is economically viable. And afterwards, we need a good ratio between purity and efficiency. So here are the solutions. The idea on the two solutions that I'm going to present to you is that we always combine a traditional process, so what we are doing today, with a new technology that will be developed for tomorrow. The idea is not to replace completely the process of today, it's to make them work together. First of all, the heavy plastic. Then we have a new technology, that's the mid-wave infrared. That's the same system that a well-known NIR system, but the idea is to move a little bit from the wavelength in order to see those black plastic. With this system, we are able to target and the PS. This way, we will remove the contaminated plastic that we send through the purification process of the Creator, and the ABS-PC can be recovered via mechanical recycling. The rest of the fraction will still be sent to incineration and landfill. Solution number 2, it's with a LIBS system. LIBS is laser-induced breakdown spectroscopy. With this system, we are going to detect first on elemental composition and then on polymer detection. The element targeted are the one listed before, and then polymer detection, we will detect ABS, PS, and PC, and ABS and PS. These are getting to the Creator process, and the rest is getting to incineration and landfill. And the ABS-PC is getting extracted via the density bath that we can see above, because it will only be remaining some technical plastic and the common plastic, such as the styrenics and the olefins. With this technique, the idea is that we can also recover more technical plastic, such as, for example, the polyamide. So what's next? Here is afterwards. So the Creator process, the fraction that were contaminated, will go through this extractive process. This is physical recycling. So the polymer is going to enter, the contaminated polymer is entering the extrusion line, and the brominated substances are removed via CO2 supercritical. Afterwards, the clean stream will still go through mechanical recycling with a normal extrusion process in order to put a granulate back on the market. So what are the impacts of all of this sorting process? First of all, on the technical aspect, we have an accurate sorting, so a precise sorting of the plastic. We increase the recycling rate by more than 45%, meaning that instead of saying the full fraction to incineration, we remove 45%, which is a huge improvement. Afterwards, we can see black plastic and we can be compliant to the REACH, POP, and ROSE regulation. From the social and economic aspects, first of all, we don't have this boundary to be linked to the fuel-based sources. That's very important. So we can implement more circular models. We are also protecting jobs within Europe by keeping this solution of sorting in Europe. We have a controlled disposal of legacy additives, so additives that are restricted within the market. We offer treatment within Europe, meaning that there is no point and not necessary at all to send any type of plastic outside of Europe. That is very important. Afterwards, we can also offer more type of plastic on the market, and we shift the vision, the mindset of the people regarding the recycled plastic from a safe secondary raw material. Our project is fully integrated in the Green Deal and the European strategy mindsets. Our idea is to release more technical plastic on the market, so more recycled technical plastic on the market, and match with 10 million tons of recycled plastic available on the market by 2025. So let's go back to our question. Is there a match between the complexity of the stream and the compliancy to the European legislation? Well, the answer is yes. There is a match with the recycling model of today, but let me tell you, we can even do it better with the recycling model of tomorrow by combining this mechanical and physical recycling, and by also recycling those technical plastic. But the key message is here. We can invest the best sorting process and the best recovery technology, but we will never reach circularity if we do not work together. It is by involving the whole plastic loop that we will be confident to reach the circularity goals by 2050. It is by establishing a transparent recycling industry with respected standards, ensuring the safe management of waste plastic. It is by strengthening our collection centers and our recycling facilities. It is by working together among R&D partners, like we are doing today, and by sharing knowledge from researchers to recyclers, including policymakers, and eventually trying to understand each other. And of course, it is with all of us, consumers, by requesting that our electronic equipment are collected, or by bringing them to the collection point, by insisting they contain recycled plastic. It is by thoroughly checking that when a substance is released on the market, as incredible as it might be, it is a safe substance to add to the plastic. So in 20 years, we do not sit together again trying to solve the same problems. Let's break this circle and build a new one where plastic does not reach the status of waste. Thank you.